once we have derived the finite difference representation for a particular method, in this case we have the forward time centered space method, we have to analyze the stability of this method in order to be sure on the convergence of the method. Remember the Lax theorem. So here we're going to analyze this stability. We're going to follow the Fourier approach, and as you see, it's very straightforward. Basically, what you have to do is to follow the receipt you derive for the Fourier approach. So here we have the finite difference representation for this method. And actually, to make the writing much shorter, we're going to call c times delta t over delta x. We are going to call beta, this parameter. So here, this coefficient we do have here, it's going to be beta over 2. So if you remember the receipt we got for the Fourier approach, basically what you have to do is we have to substitute in the numerical finite difference representation the u evaluated at n at position n and time j by this expression here, where we have some eta function which depends on k to the j power, and then times the exponential of this imaginary number, which is the I times k times n times delta x. So that's what we have to do. We are going to substitute this one in here. Okay, so if we are doing that, this is what we have. This is the expression that we have after making that substitution. And then we have to simplify as much as possible everything we have here. For example, you can see this eta to j appears in all the sides here. It's going to be simplified with this one. So just here, the only remaining eta will be here on the left here, like eta to the 1 power. Then you will see that the exponential of I times k times n times delta x also appears in all the terms here. So that will be simplified here. So considering that simplification, that this expression here becomes this one. Okay. Then just considering having in mind the formula, which basically says, I'll remember it again, that the exponential of I times alpha, where alpha can be everything, in this case will be k times delta x, will be the cosine of alpha plus I, the sine of alpha. So here, this exponential here will be the cosine of k times delta x plus I sine k delta x minus here, if we're doing this substitution here we have the cosine of k delta x minus sine minus I sine k delta x. Then because of that, the cosine of these two, they will simplify, and the only remaining one will be just the sine. So this one is just 2 times I sine k delta x. Now this 2 is simplified with this one, so that what we have here, doing this substitution here, is this eta function it's equal to 1 plus beta I sine k delta x. So this, of course, is a complex number, and we have to analyze what's the modulus of this complex number. In order to analyze the modulus of this complex number, just have in mind how do you calculate the complex of a complex number. So if you have this complex number, A, which is the real part, plus B is the imaginary component, we have that the modulus of this complex number is calculated in this way. Is the square root of A squared plus B squared. So if we are applying here, and if we calculate in this way the modulus of this eta function, this is what we have. We have that the modulus in this case is equal to the square root of 1 plus the square of the complex part, which is beta squared sine squared k delta x. So as you can see, this parameter is always, the b squared is going to be positive, the sine squared is always positive. Then because of that, you have that the modulus of eta is always going to be bigger or equal than 1 for any for all the case. So that's why, as you can see here, it's always bigger or greater than 1, which basically means that the solution we have is unstable because it will explode or oscillatory, and the system therefore will become stable for any delta t or delta x you will consider. In all the cases, you'll have that the system is unstable. And if this is unstable, it means that it becomes like that, becomes the amplitude will become bigger and bigger, so that the difference between the numerical solution and the exact solution will become bigger and bigger if you increase the time and the space, the number of time and space steps, so that becomes that the numerical method that you have developed is not useful in order to get the numerical resolution of the partial differential equation. It becomes useless.